Hello everyone. In this lecture 4, we are going to discuss about the offset QPSK. As we have studied the few topics about the QPSK, so it's a little advanced version we are going to discuss, and we are going to study about the M-ary PSK. So we know what you mean by M-ary and how we are implementing in the PSK. So that is one concept. Another, we'll just have a brief idea about the QAM. That is the quadratic amplitude modulation. So this is about this video. At the first, what do you mean by offset QPSK? The first is the 180 degree and 90 degree phase shift in the carrier phase of the QPSK can result in changes in the carrier amplitude. That is, the envelope of the QPSK signal during the course of the transmission over the channel, thereby causing additional symbol errors on detection at the receivers. So what is happening here? That the phase shift there, 180 degree phase shift and the 90 degree phase shift in the carrier phase of the QPSK, it causes the change in the amplitude level. So that causes the envelope of the QPSK signal. What is this envelope? It's like a carrier signal which is carrying this QPSK there. As we know that during the QPSK we have a two type of a carrier signal. One is the in phase and another is the quadrature phase. In phase usually uses the sign cos, and the quadrature phase uses the sine. So this together we call it as the d bits we call. So together it causes one bit or the transmission there, the 2d bits. Sorry, it's a d bits which consists of a 2 bits. So together combined it forms a envelope there. So this causes the transmission over there, and so causes some kind of additional errors to the symbol errors there. This is not possible problem in the transmission. That when we are doing it a transmission, it will be a proper. But when it passes to the channel, thereby additional errors might be added to the symbol errors there. So that causes the error. What kind of errors that we has to be rectified by offset there? How this or offset is done, and why do we require? Usually we require to cause this amplitude fluctuation. Usually the error what is happening here is the amplitude fluctuation. For example, if a two signals that are in phase and the quadrature phase in the same phase, so that time it might cause some kind of error. So it might be considered as an error there. So in order to avoid that, so we use the offset QPSK. Usually in offset QPSK, the bit stream responsible for generating the quadrature component is being delayed here. That is what this is. That delay is nothing but the offset. So what is that? The just we delay. How much it is the delay? Just a half symbol. So why this is we have done? For generating the in phase component. Usually we do it this for the in phase component. So in phase component is nothing but which is the carrier of the carrier signal of the cos 2 pi cos signal it is. Okay. So what is this? Usually cos 2 pi. The in phase component will be a general as a reference, and to that in phase component we generate half symbol delay, half a symbol delay by that we have considering in the quadrature. Remember here, the in phase component will be as normal as possible. That what we generating, that only we are giving. But when compared to the quadrature phase, we cause a half symbol delay. For example, if you have a t bit duration of t, we delay it by t by 2. So that much t by 2 delay we make, so that the d bits of a in phase and the quadrature phase is being delay of t by 2 there. If a symbol duration is t. So this is how we are generating it. Okay, so that is what I am explaining here. So what I explained theoretically, you can see it here. So pi 1 is the in phase component. This is the in phase component. This will be as normal what we had studied there, right? But what is happening here in the quadrature phase, is that you can observe it here. This you should observe this bit here. We are starting, before it was 0 to t, 0 to t, but what we are doing in the offset QPSK, we are starting it from t by 2 and ending at 3t by 2. Before it was a 0 to t, but this is what the offset how we are created is generated. You can observe it in the quadrature phase component. So it is starting at 0 and it is starting at t by 2. So t by 2 minus 0. So that is the offset there what we are generating. So like this on my offset, the phase like transition to occur in the offset are confined to the plus or minus 90 degree. Why? You can observe it here. You can see that is, see here, if this is the thing and we have a small fluctuation, so this is what the 90 degree, and if it crosses here, this is the 45 degree. So one bit is with respect to another is the 90 degree, what is the phase shift will be occurring here. So what is happening here? This is the normal QPSK. So sometimes the error noise might be compared here, but when we compare to the offset, it is as expected the plus or 90 degree, plus or minus 90 degree. So this is plus 90 degree or this is minus 90 degree. So that will be the perfect what it will be occurring. We find that amplitude of offset in the QPSK due to filter having a small amplitude than in case of a QPSK. So that's what we are assuming, that is small error you can be observed in the the normal FC, sorry, in offset QPSK the error will be very small in the small, and it will be having, we cannot say that 100% the perfect we cannot do. So small amplitude error will be there, but when compared to the normal, this is no normal QPSK, this will have a, this is offset QPSK waveform, this will have a exactly 90 degree phase shift. So exact 90 degree plus or minus 90 is there, but whereas compared in the normal QPSK it is not possible. Despite the delay t by 2 applied to the basis function pi by 2 compared with the probability of error of the offset QPSK has some probability error as that of the QPSK. So some of the errors which will be resembling the QPSK. Now we are discussing about the M-ary PSK. So we don't have too much about the concepts, just we need to have a brief idea about the offset QPSK. So now the M-ary PSK, we know about the M-ary. So QPSK is the form of a PSK. We as usually know, and we have looked into the previous videos also, lecture 1, 2, 3 also we can observe it. And also usually we refer it as a M-ary PSK, that also we call it as a MPSK. Here the phase of the carrier takes on one of the possible values of a theta 1, that is a 2 into I minus 1, that is by into pi by m, the 2 into I minus 1 into pi by m, where I is equals to 1 to m. So for example, one of the m possible signal can be represented depending on the m here. If it is a Si of t is equals to square root of 2e by t into cos of 2 pi fct plus 2 pi m into I minus 1, the whole, we call this one, where I is equals to 1 to m. So this is why, for example, if m is equals to, for example, m is equals to 3 here, okay, m is equals to 3, and so this is what I'm telling, m is equals to 3, so I is equals to 1 by 2, okay. M is equals to 3, and how much I will be here? So it will be 1, 2, 3. So here I can represent here with the 3 values. When I is equals to 1, I is equals to 2, and I is equals to 2. So this depending on this m, that much the possible can be represented there. One of the, that is the possible we can take. So what will happen here? Just see, I'll just explain the theoretical things here. And when I look into the diagram, I can explain it very perfectly. So now So this is the normal thing, 2 square root of 2e by t into cos 2 pi fct. But when you compare it, m is equals to 3 here, I is equals to 1. So 2 pi by 3, that is 60 into 2, 120, 120 into 0 here. Okay, 120 is equals to, so you can see here 2 by 3 means 180 divided by 3, 60, 60 into 2, 120, 120, 1 minus 1, 0. So the first experiment will start at a 0. Next, m is equals to 3, 120 into 1, 2 minus 1 is 1. So that is 120, 0, 120 there. Okay. Next, another. So 2 minus 1, 2 minus 1 or 3 minus 1 now. That is 2. 120 into 2. It is 240. So if you have any confusion, I'll do it like this way. When I is equals to 2, I is equals to 1. What is this value here? This value will become 0. Okay. Then I is equals to 2. I is equals to 2. So this will become 120. So I is equals to 3, 240. So again, next 120 means again what? 0. So dota, I am telling that this is a 360 degree. In 360 degree, if I get ME3 like this way, sorry, you can do it here. This is a 360, just a, please bear me for the pre-add drawing. This is 120 degree. Next is 140. This is 120. Next is 240 and next is 360. So this is how we represent. This is for 0, 120, 240. Okay, so this is how we represent. So depending on the m, we are differentiating. If m is equals to 4, what will happen? 2 pi by m, 2 pi by m, that is what? 4, 2 by 2, that is 90 degree. So 90 into first one will be 0, next one is 180 degree, next 270, next 0. Like that the calculation will carry out. So it has to be confined to a 360 degree as what we have done it for now for 360 degree. So this is how we do it. Okay, so this is how we are classifying it. So I have rubbed it because I need some of the theory parts here. So this is how we define, and this is the energy of the signal below. And also we have this function about the xc is equals to nc by t for the some integer nc there. So depending on the how much the n values to be there. So now, as we have discussed in the m is equals to 4, n is equals to, for PSK n is equals to 1 and m is equals to 2 it was. But when you go for a QPSK, we have discussed it that m is equals to 4 because we have a 4 quadrants here like this way, and n is equals to 2 because we have a 2 dimensions there. So similarly we have the two basis function like that, pi 1 and pi 2, as we have discussed in the QPSK. That is, it is one is the sine, another is the cos. The in phase component is cos, quadrature phase component is the sine. So this is in phase, that is a cos function, this is a quadrature phase function, that is a sine function. So this is how we have the consolidation form. So this is how we are doing. Now the same thing, how we the message signal has been classified, that m is equals to 3 I have shown. This is for the m is equals to 8. You can see it 1 0. So m is equals to 8 is nothing but 2 pi by m. M is 8 here, so pi by 4, 45 degree. So first one is 0, 45, 90, 135, 180, 225, 270, 315, 360. So that is how. And m is equals to 8, how is here placing? M1, 2, 3, 4, 5, 6, 7, 8. So this is how we represent it. If m is equals to 16, again here again it will get classified. And here between the message point 1 and message point, this will be the decision boundary. Message point 2 and message point 3, this is the decision boundary. And this is the amplitude will be the what is the energy of the signal, it will be, that will be the radius of the signal of the circle. And this is we call as the, and how we discuss. And look at here, that is how we call that pi by m, that's the function of the pi by m, what it is making the decision boundary between the decision boundaries here. Okay, for pi by m, how much it will be? The 180 degree divided by 8 here. So what it will be? If we calculate 180 by 80, 8, sorry, 180 by 8 here, so it will be 8 to the 16, 20. So approximate it will be in the terms of 23. That is a 22.5, because 45, 40, 0, 45. So this should be in between 0 and 45. It should be 22.5. So the 22.5 plus 22.5 will be a message 2 point, that is a 45 degree. So this is how, and this we, because of m is equals to, we call this as the octave phase shift gain. Okay, so this is how we draw it, the end use of the M-ary PSK. Now, how is the channel bandwidth? That is what we required. That was as we looked into the m is equals to n and the 8, 16 and all. This, if we carry out the same thing, so how it will be that? Okay, that is what we need to. If we can, the channel bandwidth required to pass M-ary PSK signal through an analog channel as B is equals to 2 by T, where T is the symbol duration. Depending on the symbol duration, we calculate it. But bit rate is equals to RB is equals to 1 by TB, and that is also equal to log to the base E into M divided by TB. Okay, what is this M? The M is the, what we using the M-ary PSK, that M value we have to substitute here. So now equation 1 can be again simplified as the B is equals to 2 into RB divided by log E by M. So this is what I am representing here. Okay, RB is equals to, I am representing in terms of a T here. T is equals to log to the base M divided by T B. Okay, so this is how I am representing in a TB is nothing but RB. RB is equals to 1 by TB here. So this is how I represent it here. So efficiency of the bandwidth efficiency of M-ary signal is given by sigma is equals to RB by bandwidth. That is the B here. That is again log 2 M to the base divided by 2. Okay, log 2 into log M to the base 2 divided by 2. So if we calculate here, so see, by using this, the M here 2, 4, 8, 6, 32, 64, and what is the value here, sigma, what is getting? For 2 it is 0.5, 4 is equals to 1, 8 is equals to 1.5, 6 is 16 is equal to 2, 32 is equals to 2.5, 64 is equal to 3. So what we can make an observation is that the number of states, that is the M, if M of the M-ary PSK is increased, the bandwidth efficiency is also improved at the expense of the error performance. So that we have to look at, that we have to calculate some of the factors on the error performance side. Okay, so if M increases, so the bandwidth efficiency also increases. Now another, the toy we call as the M-ary QAM. So we know the concept of a M-ary here. What is quadrature M? In a M-ary PSK system, the in-phase and the quadrature phase components of the modulated signals are interrelated in such a way that envelope is constant to a remaining constant. So that what we are using, M-ary constant is like there has to be within that same constant. We cannot vary those things. In-phase and the quadrature phase to be a constant. However, this constant can be removed as to permit the in-phase and the quadrature phase to be independent. So we can try make the in-phase and the quadrature phase independent, and we can generate a new modulation scheme that we call it as the M-ary QAM. And remember, this QAM is a hybrid form of a modulation. In M-ary PAM, the signal space diagram is the one-dimensional, whereas the M-ary QAM is a two-dimensional. So what we have, the pulse amplitude modulation is a one-dimensional, but here QAM, the quadrature amplitude modulation, is a two-dimensional. So quadrature name only suggests that m is equals to 4, n is equals to 2. So it's a two-dimensional. Okay, so what we are generating in the PAM, that is the same, we are multiplying by twice. So it involves two orthogonal band pass band, the basis functions here. Pi 1 of t is equals to square root of 2 by t into cos 2 pi fct 0, which is from less than or equal to t, is also less than or equal to t. This is the common bandwidth. But when we have used it in the offset QPSK, we had started it from t by 2 to 3t by 2. But here we are starting with the same, but we are trying to make it a independent. In a PAM, in phase and the quadrature phase time common, but in QAM, that is a quadrature amplitude modulation, we are trying to make it a independent. Let's see. Let d minimum denote the minimum distance between any two points in the QAM constellation there. Then the projection of the I message point on the pi 1 and pi 2 axes are respectively defined by ai into d minimum by 2 and bi into d minimum by 2, where I is equals to 1 to up to m. With the separation of between these 2 points in the signal space diagram being proportional to the square root of the energy, we may therefore set d minimum by 2 is equals to square root of E naught. And remember here, the pi 1, if you take it here, the vertically, the pi 2 we have to take it, sorry, this is horizontally, this is pi 2 1 will be vertically. And this distance, if this is a 0, this is 1, first point, this is second point. This is also like that. This is minus, this is plus. And here also, if we take a 0 here, plus 1, 2. Here, minus, plus. So how we are representing here, that will be the mean here. So it is the 0, d by 2, like that. Okay. Because here you can see, they have told a d minimum by this. This is the bandwidth, what is the difference between d by 2. Okay. So that is, they have, and then 3d by 2. Similarly, here also minus d by 2 minus 3d by 2. So this is as per what we are calculating. Similarly, here also d by 2, 3d by 2. Here minus d by 2 plus minus 3d by 2. So this is how we will be calculating. And when we solve the problem, it will be very useful here. Okay. So where E naught is the message and the lowest is the energy of the message with the lowest amplitude. Now, M-ary QAM signal for signal symbol k in terms of E naught is defined as, because we have two different equation, right? So Sk is equals to square root of 2 E naught by t into ak cos 2 pi fct minus square root of 2 E naught by t into bk sin 2 pi fct. One is the in phase, another is the quadrature phase here. And remember one thing, one will be the vertical, one will be the horizontal like this, so another will be the vertical there. So where t lies between 0 and capital T, and k is equals to plus or minus 1 or plus or minus 2. As I represented, this graph is same as this equation there. In M-ary QAM, the constellation of the message points depends on the number of possible symbols m. Yes, what we said m. So everything is controlled on the m. For illustration, the square constellation are considered for which the number of bits per symbol is even. So this is what we consider. Everything which will be in the square with the even number of bits per symbol. This, what do you mean by this constellation is nothing but how the ranges will be varying. As I said, for 2 will be 1, like that which will be. Okay. We write L is equals to square root of n. So this is the how we do. L is the positive integer. Under this condition, the M-ary constellation can be viewed as the Cartesian product of one-dimensional LRM PAM constellation with this with respect to the LRM PAM. So we do not worry about too much about the square matrix of this one. Okay. So A and B, there's a cos function and the sine function. So one value and second value. So that we, as I said, that is one like this way, one like this way. So this is pi 1 and this is a pi 2. Okay, when you solve a problem, you have a very good clear So this is a n number of generalized terms here, so I'll not waste much of the time here. Okay, so about this we'll solve one problem in detail, so we'll have a clean idea of how we are doing it. Next one is the average probability of error. How, if we are doing it properly, but need to have the error there. We need to calculate the error. We also know we cannot say that when we make a hybrid of this one, we need to know how this error to be found. Okay, so this average probability error can be determined by following step: the probability of correct detection, as we did it for the QPSK. That is, PC is equals to 1 minus PE dash the whole square. What is it? We can say it as a first derivative also, but we can say it as a P dash the whole square, where B dash is the probability of symbol error for the L-ary pan. Okay, this is related to the L-ary. This is one-dimensional array. Then we are not considering, but when to make it a correct decision, we are considering the array from one dimension and we are multiplying it twice there. So we'll go in detail. With L is equals to square root of m, the probability of the symbol error P dash is itself defined by P dash is equals to 2 into 1 minus 1 by square root of m into q into square root of 2 in e naught divided by n naught. This is equation 2. The probability of symbol error for many M-ary QAM is given by P is equals to 1 minus PC. That is a 1 minus P dash the whole square. So this is what I am substituting here from equation 1. But I am making it cancel each other, because assume that PE dash is small enough compared with the unity to justify the ignoring quadratic term. So again, that 1 minus plus 1 square, if you symbol it, you can see it 1 minus 1 square minus 2p dash plus plus p dash square. So, and to remove all this quadratic thing, I'll just write it as minus 2p. So minus into minus plus, so 1 and 1 get cancelled, so we need not require the square quadratic term. So I'm just, so what I am telling, that the probability of error for QAM is twice the what we are doing it for QAM. That is what I told it before also. That is, this is for one dimensional. For two dimensional, I can multiply by 2. That is 2 into this is the. So using equation 1, 2 and 3, the probability of the symbol error for M-ary QAM is approximately given by the P of equal to 4 into 1 minus 1 by square root of m into q into square root of 2 e naught by n naught. That is 4. Equation 4. This, now the transmission energy in M-ary QAM is variable. Its instantaneous value depends on the particular symbol transmitted. So therefore, probability of error is expressed in terms of the error value of the transmitted energy rather than E naught. As I said, that is we are telling in average value because of the instantaneous value depending on the symbol bit. So we cannot say what is the the instantaneous value at what time it is reaching the destination. So for that, we usually calculate with respect to the average term. So that I can represent this equation 4 as P is equals to 4 into 1 minus 1 by square root of m into q into 2 EAV into m minus 1 n naught. Okay, but what is this? The m depending on the fan, for m is equals to 4 in equation and EAV is equals to V, we find the resultant formula for the probability of error become identical to that in the QPSK. So what I'm making, so m is equals to 1, 2, 3, 4. So I'm getting a 4 quadrants. Also, we can make a cancel each other here. Okay, so this is how we are calculating. So when in brief, you can see here this 1 by square root of 4 is equals to 2, 2 minus 1 divided by 2, 1 by 2 divided by 2 into 2 cancels. So this is here. So 4 minus 1, 2 by 3. So again, this depending on the m conditions. For example, m is equals to 1, 4, O by T, so I can calculate in that way. So as we have a 2 here, because of a 2D bits, as well that will be relative, not exactly, but it will be identical to that in this one. So this matter will be like that. Okay, so at present we saw what all the M-ary QAM, the difference there. So that is the reason I made it everyone together here. Okay, so first we saw the offset QPSK, and then we had a concept about the M-ary PSK, then M-ary QAM, the probability of error we found, and we are trying to resemble all the QPSK, and we try to resemble the M-ary PSK together. Okay, thank you.